was a normal day. Sydney and Colin were sitting at their desks, working their typical 9-to-5 job, when something spectacular happened. They got a message. As the most qualified engineers in the world, Sydney and Colin were asked to help design a roller coaster for the new Seven Flags theme park.
Colin, wake up, we have to go.
Everything was going perfect until they got to the gate. It was locked. What do we do now?
Well, it looks like there's a note on that lock over there.
What does it say?
It says, find the solution of the matrix above using reduced row echelon form to get the code to the lock.
Reduced row echelon form? What's that?
I'll tell you, Colin.
Now, to begin with, we need to reduce the matrix given to us using reduced row echelon form. That means that each of the rows needs to have a leading one, and all the other factors of the matrix, except for the solution column, need to be zeros. We will start off by switching row 1 and row 2 to get the leading one in row 1. Next, we will begin a multi-step process in order to get values of 0 underneath our leading one. First, we will multiply row 1 by -2 and add that to row 2. Next, we will multiply row 1 by -3 and add that to row 3. And finally, we will multiply row 1 by -2 and add that to row 4. Performing all of these steps at once, while it can be tricky, saves a lot of time. Next, we will make the value in row 2, column 2, a leading one by multiplying row 2 by a -1. In yet another multi-step problem, we will find the zeros under our leading one in column 2. To do this, we will multiply row 2 by 3 and add that to row 3, while simultaneously adding row 2 to row 4. To get our leading one in row 3, we will multiply row 3 by -1 over 14. Next, we will put a 0 value under the leading one in column 3 by multiplying row 3 by -15 and adding that to row 4. Finally, to complete our diagonal of leading ones, we will multiply row 4 by -1/5. As you can now see, we have an upper triangular matrix. This means that all of the entries below the line of leading one diagonals are 0. Now, this is what is called row echelon form. Typically, we would solve row echelon form by using backwards substitution, but instead, we are using reduced row echelon form. In reduced row echelon form, we want all of the entries besides our solution column and our diagonal of leading ones to be 0. Sorry for the change of scenery, I had to change the paper real quick, but next we are moving on to yet another multi-step part of this process. First, we are going to multiply row 4 by -7 and add that to row 1, while multiplying row 4 by -10, adding that to row 2, and then finally adding row 4 to row 3. We are making the entries above the leading one in column 4 0. Next, we will make the entries above the leading one in row 3 0 by multiplying row 3 by 2 and adding it to row 1, and then multiplying row 3 by 7 and adding that to row 2. And there you have it. That's our solution. The solution column reads -1 0 1 2. Now, of course, we can't put a negative in our lock code, so our lock code will end up being 1 0 1 2. Look at that! Our lock opened. Now we can go into Seven Flags and build that roller coaster.
What do we need to do first?
Well, first, we need to use the gradient to find the path of steepest descent of the roller coaster. This way, we can build the roller coaster with the steepest hill to the bottom. The steeper the path, the faster you get to the bottom, and the more fun you have.
First, we need to find the path of steepest descent to find the most fun path of the roller coaster. Given the directions in the email we received earlier, we know to find the path of steepest descent of the roller coaster, given the equation W equals 2x squared minus y squared plus 8z. This equation represents the path of the roller coaster. Using the gradient will help us to find the direction of the path of steepest descent. This will be given to us in a vector value function. The formula of the gradient is given as follows. Delta W, or in most cases f, equals the partial derivative in terms of x, I, plus the partial derivative in terms of y, j, plus the partial derivative in terms of z, k. We will look at the equation again and find the x, y, and z component of the gradient. When we work this out, d dx equals 4x, d dy equals negative 2y, and d dz equals 8. We plug these numbers into the formula above and we have found the gradient. But not so fast. The gradient gives us the path of steepest ascent, but we need the path of steepest descent. In order to find the direction of steepest descent, we need to multiply the gradient by negative 1. Therefore, the path of steepest descent is delta W equals negative 4x I plus 2yj minus 8k. Wow, that was a great explanation. But now that that's done, this message says we have to find the cost of the triple helix given to us in these blueprints. Let's take a closer look.
The owner of the park has asked us to find the cost of the helix in one of the roller coasters. It is defined by the parametrized equations x equals 40 cosine of t, y equals 40 sine of t, and z equals 5t. The helix is made up of 3 complete rotations, with the cost per foot of track being equal to 1000 plus 200z. In order to calculate the cost, we must first set up a line integral that integrates the cost per foot of track over the helix, being integral of the curve of 1000 plus 200z ds. To do so, we must first find r of t, which is the component vector form of the helix with respect to t. R of t equals 40 cosine of ti plus 40 sine of tj plus 5tk. Then we must find r prime of t, the derivative of r of t, which shows the rates of change of each unknown. R prime of t is equal to negative 40 sine of ti plus 40 cosine of tj plus 5k. To find the magnitude of r prime of t, we must first take the square root of r prime of t squared, meaning we have the square root of negative 40 sine of t squared plus 40 cosine of t squared plus 5 squared. This simplifies down to ds equals 5 square root of 65 dt. Once we have ds, we can simply plug it into the original line integral with the bounds 0 to 6 pi. These bounds are found by 0 being the initial point of t, and 6 pi being the end of the third revolution in terms of radians. 2 pi radians per revolution, and 3 revolutions means 6 pi radians. After plugging in ds, you have integral of 0 to 6 pi of 1000 plus 200z times 5 square root of 65 dt. Then we must plug in z equals 5t for the z in the equation. And after that, we can factor out 5000 square root of 65, or 5 root 65 times 1000, leaving us with 5 square root of 65 times 1000, all times the integral of 0 to 6 pi of 1 plus t dt. After that, it's simply a matter of solving a regular integral. you end up with 5,000 square root of 65 times t plus t squared over 2 from t equals 0 to t equals 6 pi. This results in 5,000 times the square root of 65 times 6 pi times 18 pi squared, which results in the end cost of the helix being just about $7.9213 billion, or 7.9213 times 10 to the 6th.
Finally, we have to calculate the curvature of the triple helix.
We want the triple helix to have a small curvature because if the curvature is too large, the roller coaster will have too sharp of a turn and the cart could fly off the tracks.
The park owner has also asked us to calculate the curvature of the helix. This is much simpler after having found the cost, as many of the steps are the same. We must first find r of t, r prime of t, as well as the magnitude of r prime of t from the same equations as before, so we simply reused what had already been written. After this, we must find t of t, or the tangent vector at point t. To find t of t, we must first divide r prime of t by its magnitude, resulting in t of t equals 1 over the square root of 1,625 times negative 40 sine t I plus 40 cosine of t j plus 5k. After that, we must find t prime of t, which is equal to 1 over the square root of 1,625 times negative 40 cosine of t I minus 40 sine of t j. Then we must find the magnitude of t prime of t, which is equal to the square root of 1 over the square root of 1,625 squared times negative 40 cosine of t squared plus negative 40 sine of t squared. This results in the square root of 1,600 over the square root of 1,625, which is equal to 8 over the square root of 65. In order to find the curvature, we must have the magnitude of t prime of t divided by the magnitude of r prime of t. This is equal to 8 over the square root of 65 divided by 5 times the square root of 65, which is the same as 8 over 5 times 65, or 8 over 325, resulting in a curvature equal to 0.024615.
And we're done! You're looking at the two newest roller coaster engineering extraordinaires, and we couldn't have done it without your help. Thanks for watching!